Howdy gamers, how is everyone doing this Sunday evening? I hope everyone's doing all right here. Hello everyone. I see we have GT student in the chat. Hello, hello. Yes, today's Sunday, so that means we're going to be starting off with our little math office hour thing. So I know I had two questions asked today, so I know one of them was by you, GT student. I know there's one other. I'm not sure if they're here in the chat now. And welcome in Puffin as well to the stream. I know you're not here for math stuff, Puffin, but I hope like you can also enjoy our little office hour here as well. So the way this is gonna work, let me move over to here. Okay, here we go. Okay, where is this bird thing? A Twitch provided filter? No, this is I did have yeah. So this is like a 2D model that I had made by some artists. If you're interested in the artist that made this, I do have a link, I do have a link in my about section under credits, and you can look up the artists and take a look at their work. But they do have but yeah. How did you get it to sync with your mouth movements? That's a good question. So the way this works is so the way it works is this. Yeah, so an artist, basically they make a model, and they basically have to do something called like rigging the model, which basically specifies like the shape of like the mouth for different, say, like vowel sounds like A, E, I, O, and U. And then from there you use another program. So the program I use is called Vtuber Studio, and the way that works is so right now I have my laptop webcam. And it's just basically doing like face tracking essentially. So it's just looking at my face and looking at the shape of my mouth, and it's using that to determine and that combined with the rigged model to determine what shape like the mouth should be, and also like the position of the head and like the eyes blinking and whatnot. So yeah. Yeah, I so it is pretty interesting stuff. It's pretty neat, I will say. There are other ways. So there's multiple ways that people get this to work. So for the mouth movement in particular, some people use face tracking, and some people use there's other programs where instead it takes like the audio, and it infers your mouth shape based off of the audio input instead, which can be more or less accurate depending on the quality of the mic. My mic quality is not that great though, so I'm basically just using the facial tracking to do the lip movements. Let's see. Okay, there we go. So I have OneNote open here. Let's see. So I know we have. Do we have the other person in chat here, or is it just? Let me see. 1 second. Okay. Well, if the other person comes in chat, because I feel like your question, GT, was a little bit more open-ended. So I was going to start with the other person's question first, because I feel like I'd be able to more easily answer and wrap that up. But if they're not here now, we can start off with your question, which is, you know, kind of going over like the idea of modular arithmetic, right? So I think before we talk about like what modular arithmetic is, I think it's good to talk about the idea of 1 second, this cord is in the way. I think it's a good idea to talk about like the notion of what's my pen not working? 1 second. There we go. Talk about the notion of an equivalence relation. Right? So the idea of an equivalence relation is, right, we have like, so in math, right, we have like this notion of like equality, right, where, you know, like two things can be equal to each other, but sometimes we want to have like a looser version of equality where things are like kind of equal to each other, or like maybe like equivalent to each other but not quite equal. So let's just maybe very quickly go over kind of this notion of an equivalence relation. I think that's a good thing to start with here. Right, so I think maybe one example, right? Say like I have say like I draw a triangle, for example. I draw this triangle, and then, you know, maybe over here I'll draw like this triangle here. Let me try to actually let me do this a little bit better. Let me just let me do this. Let me just take this and just copy it over. Now you might ask, like, are these two triangles equal, right? So if I label this, say, triangle 1 and triangle 2, I can ask, you know, are these two triangles equal? You might be tempted to say yes, right? Like they're the same shape, but what if, I mean, but say like I put this like on a coordinate grid now, right? Say like, oh, I have like some coordinate grid, you know, this is like X and Y. Now you might be tempted to like, oh, well, maybe they're not the same triangle, right? Because they're like in two different positions in space. But in a sense, they're the same. I mean, even though they're not equal in the sense of being in the same exact position, right? They're like equivalent in the sense that we know that you can say like go from one to the other by simply translating the triangle, right? So even if they're technically not equal, we can see that they are. We're gonna use this notion to mean that they're equivalent, which is like a somewhat looser idea of equality. It's like, okay, maybe these aren't the exact same thing, but they're equal. They're equivalent in some sense, right? So it's like a looser notion of equality. So one thing to remember for an equivalence relation. For an equivalence relation, you know, if you say we use these three bars, it satisfies three important properties. Right. So the first one is reflexivity. Oh, by the way, if you have any questions. Does an equivalence relation have to be looser than an equality? Well, so in a sense, essentially that's what it is, right? So, I mean, you can have different degrees of an equivalence relation, and the most, yeah. So right. So they're kind of different extremes, right? On one extreme, you could like consider everything to be equivalent, like everything in the world, just say everything in the world is equivalent, but that's not very interesting, right? The other thing you could say is like, you could just say that each element is only equivalent to itself if it's equal to itself. So usually we want to consider things that are in between those, and you can kind of think of equivalence relations as like a yeah, it's kind of like a way of defining inequality. So these three properties that we're going to look at, they're basically properties of equality that you see, right? So we know, yes, let me write this here. We have reflexivity, right, which just says that anything has to be equivalent to itself for all x. It has to be symmetric, which says, like, right, if x is equivalent to y, then it better be the case that y is equivalent to x, right? So notice, like, these properties are also properties of equality. So we're saying that these properties of equality are kind of like the fundamental properties of equality. So this notion of equivalence should also satisfy these three properties. Let's see. All right. Sometimes my cursor disappeared and it's difficult to see where it is. Here it is. Okay. And then we have transitivity. Or if my handwriting is also not the greatest. So transitivity says that if x is equivalent to y and y is equivalent to z, then x is equivalent to z, right? So this last one is just basically saying that, so we know, like, equality, you can kind of chain together equalities, right? And so the same thing is a property that you have with transitivity, right? So these are basically the three properties of an equivalence relation. And basically what we're going to show is, like, this notion of modular arithmetic actually satisfies these three properties, right? So in a sense, when we do modular arithmetic, we can kind of think as certain numbers being equivalent to one another, even if they're not technically equal to one another. Right? That's kind of the kind of cornerstone, or kind of the important aspect of modular arithmetic is like we can treat numbers as if they were other numbers, right? So with modular arithmetic, where'd my cursor go? There it is. For the real numbers, are the reflexive property and the symmetric property basically the same? I'm not quite sure what you mean with that question. So I mean, so these are two distinct properties, right? This first one is just basically saying, so if you think, for example, equality on the real numbers, right? This is just saying every number is equal to itself. And this one is basically saying, so you can imagine this one is saying, like, for example, like, if 1 plus 1 equals 2, then 2 equals 1 plus 1. But yeah, so I mean, yeah, so they are technically different properties. I mean, like, equality, yeah, equality is you can kind of think of equality as, like, the most extreme equivalence relation, right? Because the only things that are equivalent to other things are the exact things itself, right? It's a bit of a weird, or yeah. So you can think of equality as the most extreme case of an equivalence relation. Okay, so moving on to modular arithmetic. Right, so now we're going to define this equivalence operator in the context of modular arithmetic, right? So we kind of saw it in the context of, like, geometric translations, but now let's see it in the context of, actually working with numbers here. Okay, so yeah, modular arithmetic, it is really cool. Like, I swear to God, it's like magic sometimes. Like, the things, right? It's kind of cool. Like, even though, like, numbers are different to one another, in certain scenarios you can kind of treat them as all the same number. Okay, so actually let's try to define. So we're gonna say that x. So I should say this is all. We're gonna work in the context of integers for the rest of this discussion here. You can kind of define like the modulo operator for real numbers, but we're just gonna stick for it with integers just to make this discussion a little bit easier. So we're going to define this, the mean. We're gonna say, like, this is equivalent to saying that Yeah, so maybe let's say modulo m. So usually when you do modular arithmetic, you're doing it with respect to some modulo integer here. So for example, say if you're doing stuff with like say time, you know, like there's 24 hours in a day, so you'd be working like modulo 24. So in other words, when we work say like modulo 24, right, the only numbers we consider are right, you can kind of think of like, okay, you go from 0 up to 23, and then once you hit 24, you loop back around to 0 essentially. So let's go ahead and define what we mean here. So we say that I want to use this little m here just to make it clear that we're working modulo m. I'm just going to put like a little m by this bar here. I think that might make it a bit clear. The modulo m. So we're going to say x is equivalent to y modulo m if x and y have the same remainder after dividing by m. All right, so this is kind of, we're kind of saying it in words here, but basically this is what we mean. If x and y have the same remainder after we divide by m, then we say that they're equivalent. Right? And then this is like a really useful notion, right? Right, so kind of going back into like the hours in a day example, for example. So say it's like, you know, that's an example. So 3 this is equivalent to, one second here. So maybe this might be a good example. Can I get this? Sorry, I'm having some technical difficulties here. Yeah, so yeah, good. That's a good point there. Okay, maybe I'll just start with that example first. So 3, this is the same thing. This is equivalent to 27, exactly. Right? So for example, if I told you, oh, like, you know, 27 hours from now, blah blah blah, right? Then if you wanted to like to know like the time of day, right? You can divide out the 24 hours, and you know that's like, okay, well that means I know that I can just look at the next day, and I know I need to just go 3 hours from now. So for example, like, you know, if it's like 5 p.m. then in 27 hours it will be 5 plus it's going to be 5 basically, right? You have like, you would add the 27, but since we're working like modulo we already like, right, 5 plus 27, this is the same thing as just 5 plus 3, which is 8, right? So right, you would meet me at 8 p.m. the next day, right? so like knowing how to reduce numbers like modulo other numbers can kind of help you, right? You're kind of saying like, okay, if all I'm interested in is like the time of day, right? I can then I know multiples of 24 don't matter, right? I can just like cancel all those out, because those are just looping the days around over and over again. And I just need to see what's left over, right? So there's some interesting properties of modular arithmetic that are worth noting here. Well, so first of all, modular arithmetic satisfies the 3 properties of an equivalence relation. Right? I mean, if you think about this, like that kind of makes sense, right? So if I say, if I look at this statement, and okay, I can ask like, okay, does any number and the same number have the same remainder after dividing by m? That the answer is yes. Like I'll say, if x and y have the same remainder after dividing by m, then y and x have the same remainder after dividing by m. And then for this transitivity, right, we can say if x and y have the same remainder, and if y and z have the same remainder, it's not right. Then it has to be the case that both x and z have the same remainder after dividing by m. So it's hopefully it's pretty straightforward to see that, right, this kind of statement here satisfies all three of these equivalence relation properties. So another cool thing about equivalence relations is that they allow you to, so we can say that certain numbers are equivalent to another, but they also allow you to kind of group the numbers into groups. Is a commutative property of addition an example of symmetry? Yeah, so that's a good, so that's a slightly different, so that's like an operation that's, so it's important to remember, so this isn't quite an operation. This is kind of saying, we're saying like this x and y is related in some way, but that is a good point though. Like that the addition operator is symmetric. Like a plus b equals b plus a. But yeah, there's a slight difference between, say, looking at like a relation, which is where a relation just is either a relation is like true or false, right? I have like x is equivalent to, or these things are either true or false. Whereas with an operation like addition, where you actually output like a number of some sort. Okay, so I want to look at another example here. Where's my cursor? There it is. Okay. So let's consider numbers modulo 3. Right, so I'm just going to start listing out the numbers here. So I have like 0, 1, 2, 3, 4, 5, 6, 7. Over here, like -1, -2, -3, -4. I mean, these keep going, but I'm just going to list some of them here. Right? So I'm going to, let me switch colors really quick. First, let's look at 0. I want to start with 0 here. You have 3 groupings, right? So let's first start with 0. I can look at everything that's equivalent to 0, right? So, right, the remainder of, right, divide by 3, the remainder is 0, right? So what are some other numbers that are equivalent to 0 modulo 3? Yeah, basically all the multiples of 3, exactly. So if we do that, I'm going to circle all of them here. Do all of these. And then I can say, I can look at, let's look at, say, 1. I can ask in red, like, what are all the things that are equivalent to 1? Well, it's going to be 4 and 7, right? If I divide any of these numbers by 3, right, I get the... Does Switch have latex built in? Unfortunately, it does not, at least not to my knowledge. It would be nice if it did, but I don't think it does, unfortunately. Okay. And then lastly, I can look at, say, 2. Right? And the things that are equivalent to 2, well, it's going to be 5, let's see, -1, and -4. So one neat thing here is that there's kind of 2 things, right? These colors, right, like, none of the blues overlap with the reds or overlap with the greens, and furthermore, every single number belongs to one of these 3 groups, right? So it's kind of an interesting property we have there. So what I can say, I can consider like these, like the different sets, right? I can consider 0, 3, 6. I can put these into 3 different groups. -4, -1, 2. Oh, let me. Sorry, I was looking at the wrong. I want to put these in order. I think that'd be a bit better here. Okay, so I have. Okay, let's look at the red ones. -2, 1, 4, 7. And then lastly, Penguin Bucks. That's a good question. So, on Twitch, you can earn points by basically just watching the channel, and other things as well, like following. You can earn points, and then if you accumulate enough points, you can get certain rewards that you can redeem on the channel. There's a few of them listed there. If you click on the little icon, I believe it should pop up like all the different rewards that you can possibly get. Okay. Where were we? So, and then lastly, we have everything in green here. So we have a -4. We got -1. We got 2, 5, and so on, right? So I have these 3 different groups, right? So basically, I've taken every single integer and I've put them into one of 3 groups. What I can do is I can name these 3 groups. Let me get rid of this line there. Okay. I can give a name to these 3 groups, and the way that I'm gonna do that, I'm just gonna pick a representative, one representative from each group, and it doesn't matter which one, but I'm just gonna pick one. I'm gonna call them in this way. I'm just gonna put the brackets just to denote that the brackets indicate not the number itself, but the entire group, right? So normally in a modular arithmetic class, you don't really deal with these brackets, but you should pretend that they're there. You should pretend that these brackets are there, and that when you write 0, you really mean 0 and everything that's equivalent to 0. And the nice thing is that if you think about it this way, you can think of this as a placeholder, which allows you to basically replace this with whatever you want. So 0, I can also say this is the same thing as, say, 3, 6. So all I mean here is, like, I'm just saying take this number and look at everything equivalent to it, right? So by thinking of modular arithmetic in this way, you can think of each number as not really a single number, but really a collection of numbers. Hopefully that makes sense. So the cool thing about this is, really, the cool thing is, like, really there's only, right, if you think about modular arithmetic, right, we've taken an infinite number of numbers, but there's only 3 groups. Oh, holy heck, thank you, Tayuni, for the raid with 32 raid. Oh my gosh, hello everyone. This is crazy. Welcome in. This probably is, well, yeah. How is your stream? This is yeah, there are raids. I was not expecting a raid this big. Hello, welcome. How are you, Tayuni? Let me give you a quick shout out over here. This is great. You caught me at an interesting time. I'm actually doing like a little like office hour math thing, but we're actually going to be doing a little bit of Mario Golf after this. But thank you for coming in. Those of you that aren't aware of my channel, I am Penguin. I'm a Penguin Vtuber, as you can see. I play a lot of platforming games, and I play a lot of office hour math as well. Oh, really? Oh, nice. That's interesting. Yeah, so I'm basically every Sunday at 10 p.m. I do a little math office hour here. So that's exactly what I'm doing. So that's actually pretty interesting. Wow. They like host but one time. Okay. So yeah, as you can see, we're just answering some questions about modular arithmetic here. Kind of just going over the basics here. And then those of you that are also interested possibly in my gaming content, I do play like platformers, and we're doing some Mario Golf after this. So if you want to stick around for that as well, feel free to do that. But thank you so much for the raid. I really appreciate it. Okay, so where were we at? We're talking about modular arithmetic here. So we have, yeah, so we've taken basically every single integer and we've broken them down into 3 different groups, right? So we can kind of essentially think of, you know, modulo 3, there's only, right, if you think of these groups, right, you can just think of just working directly with the groups themselves. Essentially, there's only 3 elements that you have to work with. Thank you so much, Ty. I gotta eat dinner. I hope you enjoy it. Have a good one. So let's maybe think about a few things, right? So we have, so modulo 3, we essentially have 3 elements, or 3 groupings, right? We have everything that's equivalent to 0, everything that's equivalent to 1, and everything that's equivalent to 2. How do you spend channel points? GT, you should be able to click the little penguin bug icon. If you click that, that should bring up a menu of all the things that you should, all the possible rewards. And if you click on the rewards, it should give you a brief description of each one as well. Okay. Yeah, these are just, yeah, these, I mean, you can think of the, yeah, so these are the equivalence classes, essentially, yes. You can also think of them, so you can also think of them as like mathematical objects that you can work with directly as well, right? So one thing you might add, thank you for the yay. Just plays yay. Some of those sound alerts are very helpful or can be interesting to use in certain situations. Okay, so where were we? So one thing we could do is we can maybe ask if we can make like an addition table for this, right? We can add these equivalence classes with one another, right? So there's only really 3 elements, so you can kind of like make a little addition table here, and then ask like, okay, well, what are these? And the natural way of doing this, basically, that's way too loud. Jeez. Can you add equivalence classes? Let's see. I'm not sure what you mean. So I have written so right now we're just discussing just the general properties of equivalence classes. Yeah. So for those of you that are just coming earlier, we did discuss kind of what an equivalence relation is. Right. It's basically something that satisfies these 3 properties: reflexivity, symmetry, and transitivity. And basically, we can think of it as a more looser version of equality, right? So there's this notion of things being equal to each other. For example, these 2 triangles here, right? They're maybe not exactly equal because they're in different locations, but we can consider them maybe equivalent in the sense that you can get from one to another by some transformation, right? So we've been looking at this notion of equivalence classes for modular arithmetic. And then what we can do is we can, we only have 3 equivalence classes now. So what we can do is we can actually like fill in an addition table for these. And what we can do is actually, we're going to do this in the, so how do we, so you might ask, okay, so how do I want to define A plus B here? Right? So the most natural thing you might think to do is like, well, let's just take the representatives inside and just add them together, right? So we can do that exactly here. So let's just do that. So 0 plus 0, that's 0. 0 plus 1, that's 1. 0 plus 2, that's 2. 1 plus 0, that's 1. We have 2. So now we get into an interesting situation here, right? I can take the equivalence class with 1 and the equivalence class with 2. I can ask, okay, well, what happens if I add those together? So I get 3, but this is also, remember, this is the same thing as 0. So either of these, right, are fine. If we want to represent everything in terms of only 0, 1, or 2, then we could just write 0. But remember, these are essentially the same thing. Yeah. And then here we have 2. Here we have 3, but remember, this can be rewritten as these equivalence classes are the same. And then lastly, we have 4, but remember, this is equivalent to the 1 here. Yeah, so you can kind of think of it as you're asking, oh, why is the equivalence class of 3 equal to the equivalence class of 0? So that's a good question, Lazy. So if we look at our diagram here, right, what we did is we took all of the integers, and we looked at 0 first, and we asked, what are all the things that are equivalent to 0 modulo 3? So here we're in this example, we're working modulo 3, just to clarify. And by equivalent, we just mean what are the numbers that have the same remainder after we divide by 3, right? So 0, if we divide 0 by 3, the remainder is 0. If we divide 3 by 3, the remainder is 0. If we divide 6 by 3, the remainder is 0. So all of these blue circles, they're equivalent in a sense, yes. They both yield a remainder of 0 when divided by 3. Yep, exactly. So the equivalence class of 0 are all of the, basically multiples of 3. The equivalence class is 1 is basically all the multiples of 3 plus 1 more. And lastly, the equivalence class of 2 is basically all the multiples of 3 plus 2 more. Oh, hello, Kaho. Thank you for the raid of 1. Welcome in. Hope you're doing well this weekend. As you hear, we're doing math. I'm not sure if you're here. Yeah. I'm not sure if you're here to see some math, but I hope you enjoy the coming on in, Kaho. Thank you. Okay, so we have this idea. You started doing math and you had to. Jeez. Yep, we're doing math. Yeah, so we have this notion of addition of equivalence classes, and we also have this. We also can do the same thing with multiplication, right? I can ask if I multiply. Yeah, I did teach you. Yes. So, is that operation true for all numbers? Oh, are you saying is this notion of addition, like that we do? Yeah. So this does generalize. Right? Here we're working modulo 3, but this process that we're doing, we could do that. You can do this modulo whatever, right? It doesn't matter. Essentially, you can. So say if you're doing modulo 5, you would be able to group the numbers into 5 different groups, and the elements would be the equivalence class of 0, 1, 2, 3, and 4. Yep. And then you can do the same kind of operations of addition, and we're also going to define multiplication in kind of a similar way. We're going to basically take the insides and just multiply them together. Right? Can we take any two numbers of both of these math? Yeah. So there's kind of an interesting thing here. Like this, you might ask, like, is this? There's a good question here. It's like, is this well defined? Right, because the thing that we're doing is like we're determining the output based off of, right, because these things are mathematical objects themselves, but we're somehow using not the object but the representation of the object to arrive at an answer. You might ask, is that a valid thing to do? Oh, bravo! Is there a whole class here? There's not a. Well, interestingly, I did get a raid earlier from someone that also does like a math office hour thing. So I guess we kind of do have, so I don't know if everyone here are part of the same class, but we have, I guess, roughly a class size here. Lazy, yes. So yeah, well defined. You might ask, hey, what does well defined mean? So back to what I was saying here. So maybe let's give an example. So notice. Say I did like say the equivalence class of 1 plus the equivalence class of say 2, right? We know this is going to be 3, which is 0, right? But notice but the thing is, this answer that I got depended on the representatives I chose, right? What if I chose something else? Notice, like, right, this is the same thing as say 4. This is the same thing as, say, let's see, this is the same thing as, say, like, -1. Right, so you might ask, okay, well, if I take these representatives, or if I switch out the representatives, if I do this, do I get the same answer? Right, do I get back to the same answer of the equivalence class of 0? And the answer is actually yes. You actually do get the same. So if we actually carry out this result, right, we just get we actually get the same. We get 3 again here, and then we get this is 0. but it's not actually clear that this should always be the case. This is something that you do actually need to check. Let me look at some questions here. The true for all of the domain. Yeah, so the result of addition is independent of the choice of representatives. Exactly, yes. So as you see here, even if we swap out the numbers, the result that we get is still going to be the same, right? Which is kind of a very good property to work with. So that means, say, if you're working with modular arithmetic and you're doing like these multiplication and addition operations, this is just by saying that it's well defined, what we mean is that you can always swap out any representative with any other representative, and you would still arrive at the same answer, which is a very useful property to keep in mind. So maybe we can go over some examples where that might be useful, for example. So actually, maybe we can do. So maybe what I'll do is, do you guys want to see a proof of this, like a proof that this this operation is actually well defined? I'll leave that up to GT since he is the one that did request to go over this. Okay, sure. Okay, so let's go over that. Oh, thank you. Okay. So what we want to show, let's see. So here's our claim. So suppose that A plus B equals C. You're going to call this A1 and B1. And suppose that A1 was equivalent to A2, and B1 is equivalent to B2, right? Then my claim is that I can swap out A1 and B1 with A2 and B2, right? In other words, I can just swap out the representatives. And I still get the same answer of C. So that is the claim. Jesus Christ. Yeah, so Lazy, you could yeah, so you could try to do that kind of like with just the multiples of 3, but we're going to try to show it in general here to show that you know, regardless of like the modulo operator that we're using, that this does work. Or I think for this math office hour thing, I think I'm going to hold off on that particular redeem for now. Sorry. I think I would be very distracted if I tried to do that, unfortunately. Okay. So let's actually try to show this claim. Hopefully the claim itself is understandable, right? We're just saying if we have this result and we swap out A1 and B1 with A2 and B2, the result is still the same. I will give you a refund, don't worry. Okay. Where were we? Okay, so let's think about what all of this means here. Okay. So so first, so proof, where am I? Where's my cursor? Proof. So yeah, so we have that A1 plus B1 equals C1. But remember, right, by our definition of how we're adding things, right? This is just, oh, where's my eraser here? My bad. By our definition of addition, right, this is just A1 plus B1 equals C1, right? Hopefully this makes sense. Remember, this is just a definition of how we've defined addition for equivalence classes. Right, but what does this mean? This is saying that this number and this number belong to the same equivalence class. Yeah, so GT, one way to support the channel, so on Twitch there's something called subscriptions where you can subscribe, which does, you get some benefits such as being able to use emotes on the channel, and also it does help somewhat financially with the channel as well. And if you have Amazon Prime, you're able to basically give a Prime sub, which is basically a free, one free subscription that you can use every month. You don't get how... Okay, so remember this is how we're defining, right? So we're just defining... We've defined addition and multiplication in this way. Where we're just saying like, we've defined the addition of equivalence classes. They're just saying we're going to add the representatives. Does that make sense? So in particular, like these two additions are two different additions. This first addition is addition of equivalence classes. The second addition is just regular old integer addition, right? So I should maybe use two different symbols. Oh, thank you for the follow, Bepis. Is that how you say it? Bet these. I hope I'm saying that right. But again, same thing over here. These two multiplications are different. This is multiplication of equivalence classes, and we're defining that in terms of multiplication of the integers themselves. So remember, so now we're saying that this number and this number, that these two equivalence classes are the same. But remember that two equivalence classes are the same if the numbers basically have the same remainder, right? So this is the same thing as saying that A1 plus B1 and C have the same remainder after dividing by m, right? Hopefully that makes sense. So we have this here. Okay, so we're actually not too far away from what we want to show, right? So let's see, how do we want to write this? I'm trying to think of the best way of writing this so it's not too long. Here, okay. I'm going to make a little side note here. This is just to make things easier for us. Is it sufficient to swap out one of the operands to prove the statement instead of both A1 and B1? Well, so kind of right. The whole point of this is we're trying to show that we can swap out A1 with A2 and B1 with B2 and still get the same result, right? That's kind of the thing that we're trying to show here. But I think, okay, so I think the easiest way of doing this, I wanna write this. If this claim doesn't make sense, I can elaborate further. But this number and this number having the same remainder, I'm gonna claim that if this is the case, then A1 plus B1 minus C is some multiple of m, right? So I'm gonna say I'll just say this is Km. Does this make sense? Right, so just imagine like two numbers that have the same remainder, and if you were to take their difference, right? So you might have seen like the if you write this out like in terms of like a quotient and a remainder, and you take the difference, right? The remainders would cancel out. You're both confused and interested. Hello, Captain. Thank you for the follow. Yeah, I understand. Like, if you're just hopping in, it can be a little bit confusing if you're hopping in, just kind of in the middle of our talk or discussion here. I can understand. So basically, what we're trying to do is we're just discussing this notion of modular arithmetic, which in a sense is kind of like clock arithmetic, where we can think of numbers being equivalent to other numbers. So, for example, right. You know, it's like say 3 p.m. on a clock or in the day, but then like 24 hours later, right, it's still 3 p.m. I'm gonna think, oh, what about 25 hours later? Well, you could, you know, you're not gonna say 28, you know, o'clock or whatever. you would just you would loop back around. So a lot of this stuff is helpful in like situations where we don't care about like where we want to think of some numbers being equivalent to other numbers here. Okay, cool. So we have this. So another thing that we can say is that what am I trying to say here? Okay. I want to write this on the side here. This is probably going to be helpful. So I have that a1 minus a2. This is some other multiple of m. And b1 minus b2. I'm running out of letters here. I'll use d. This is some other multiple of m. Good? Okay. Right, so where am I getting these from, right? So remember, we know that a1 and a2, they are equivalent. So that means that they have the same remainder, which means that if we take their difference, it's going to be a multiple of our modulo m here. Same thing for b1 and b2, right? They're both equivalent. That means that they have the same remainder, and this means that if we take their difference, that should also be a multiple of m. Now what I can do is I can so notice I can solve this for a1, right? a1 is equal to a2 plus lm. b1 is equal to b2 plus dm. Now I can plug this into here for a1 and b1, and what do I have? I have a2. I'm going to kind of rearrange the terms a little bit, but I have an a2, a b2, plus an lm, plus a dm, minus c equals km. I'm going to rearrange this a little bit more. So this is just kind of algebra at this point. I have a2 plus b2 minus c is equal to, so I'm going to move this lm and dm to the right hand side, and I'm also going to factor out an m. So I'm going to have an m on the outside. I'm going to have a k minus l minus a d. So this is just algebra that I've done here. Hopefully that's made sense so far. But now notice what do I have? I'm pretty much done, right? Because what have I shown? I've shown that this number and this number is a multiple of m. I mean, this is some stuff here, but all of this is just one integer of something. The right hand side is a multiple of m. So this means that this number, a2 plus b2, is equivalent to c, right? And that's exactly what we wanted to show. So hopefully that makes sense. So all we did was like we basically just we kind of shuffled a lot of things around algebraically, but in the end we know that it works, right? That's kind of the gist of it here. Are there any questions about this proof? If anyone has any questions. Yeah, so just to summarize the result again, right? What did we show? We showed that when it comes to modular arithmetic and we deal with addition, we can always swap out any number with any other representative and we get the same result. And this is the idea of being well defined, exactly. And I'm not going to prove it for multiplication, but the proof is going to be similar, right? You would do this kind of same thing here, where you kind of right, you can combine the equivalence classes in a similar way, write out what right, these quantities here, kind of plug in things algebraically, and it should work out. But yeah, we do have the same result that shows that multiplication in this way is also well defined, right? All we're saying is like you can multiply equivalence classes, and it doesn't matter what representative you choose on the inside, you still get the same answer regardless. Okay, so let's maybe look at some ways in which these properties are useful, right? So let's say, I'll try to do an extreme example here. So let's say you wanted to know, let's see, what Ba-ba-bum. I'm trying to think of a good example here. Okay. Yeah, so let's try. We'll do an easy one here. This might look hard at first. Let's say we have like the number 99 raised to the 10th power, right? And we want to know, we want to know what this is equivalent to if we work modulo 10, right? So we want to work, sorry, not modulo, I'll also work modulo 100. Right, so in other words, we want to know what the remainder is after we divide by 100. So I mean, so one thing you could do, right, is you could multiply 99 by itself 100 times, right? But that's not really great, right? So what can we do? I'm going to consider, instead of 99, I want to consider like the equivalence class of 99, right? So 99 to the 10th, what is it? This is just the same thing as saying 99 times 99, right? 10 times. Good. But now look, now this is just all multiplication of equivalence classes here, right? This is just all multiplication of equivalence classes, which means that I can swap out any of these representatives with any other representative, right? So what is another representative of 99? Can anyone tell me? So remember, we're working modulo 100. Yeah. So in one direction, yeah. So I can add 100. I can get 199. What if I go the other way? What is the number that's smaller than 99 that's equivalent? You know, so, well, yeah, -1, exactly. So we have, so I can actually replace all of these with -1. I have this 10 times. Right, and this is, remember, this is because the equivalence class of 99 is equal to the equivalence class of -1. So I've just replaced these. There is a bit of lag between chat and show up on your page. Yeah, I know. Unfortunately, like on Twitch, there's always going to be somewhat of a delay. Unfortunately, I know it's gotten better over the years, but that's kind of just the situation there. But again, look, now we've actually reduced this problem to one that's a lot more manageable, right? Remember with the definition of equivalence class, I could just combine all of these, right? I can just multiply the representatives. I have -1 times -1 times -1 10 times. Right, but this is just equal, like -1 10 times is just going to be the equivalence class of 1. Yeah, so 99 to the 10th isn't divisible by, yeah, it's not divisible by 100. No. And we see that this answer is actually going to just be 1. Right, so in other words, if you were to divide by 100, you get a remainder of 1. Or in other words, right, if you think about, right, we work in a base 10 system, so this is also just saying that the last two digits are just going to be 0, 1. If you look at this result here, so this is kind of like a very powerful technique, right? Because, right, I could have I wrote 10, like I could have written like, you know, like 1,000 here, right? And all of this would still work here. Notice we're kind of using the fact that we have like an even amount of negative signs that cancel to give us 1. If this number was, say, like if I had like an odd power, like say like 5 or 1,001, then we would get a remainder of -1. But in any case, we see that, right, we've reduced this problem to one that's a lot easier to work with, right? because like multiplying 99 by itself 1,000 times and then trying to take a remainder, right? That's not very feasible. But we see that if by working with, the numbers that are equivalent to the 99, modulo 100, then we've reduced this problem to one that's a lot easier to work with. Are there any questions about this example? Okay. Okay. So I know that usually my office hour that we do on Sundays usually ends at 11. So I do want to wrap things up, but I do want to ask if there's any last minute questions from GT or anyone else that's watching. I would like, if there are any other questions, I would like to stay on topic regarding modular arithmetic here. But otherwise, thank you for the hydrate, Captain. Appreciate it. Actually, I do have a little water bottle. Let me show you guys. Here we go. I got some water here. Been talking smart a lot. I need to hydrate. Yeah, my mouth is getting a little bit dry from talking. It's funny. I know like a lot of people say that like streamers, they're talking constantly, but I think that I swear like teaching involves even more talking than just streaming a game. I swear. This is fancy water. You got the fancy, not Fiji but DG water. Yeah. Oh gosh. Okay. Thank you for the hydrate, Redeem. Okay. We have. You're good, GT. Yeah, no problem. Again, if you have any questions, feel free to come by next Sunday. We'll be doing this again at 10 p.m. Eastern, 10 to 11. And thank you again, Raiders, for coming by as well. If you're curious, so I do these office hours every Sunday, again 10 to 11 p.m. Eastern Standard Time. And the way that this works is I have a Discord server, and people are free to ask questions in there. So if you ask questions in there, then I'll take a look at them and answer them on stream, basically. Although, yeah, I do usually ask that people ask their questions ahead of time, just that way I can more easily prepare. My major, yeah. So I'm actually currently a PhD student. I did my undergrad in math and computer science. Right now, I'm working on kind of like combinatorial optimization problems. So that's kind of like a lot of stuff like involving graph theory. And I'm also looking at that and the overlap with like quantum computing. I haven't done too much quantum computing. That's kind of something that's new to me, but I'm trying to learn a little bit about that and how that can be applied to optimization problems like that are interesting from a combinatorial perspective. If you guys have questions about that, I'm also happy to answer those. Yeah, watch streams with Cool Penguin and learn. Yeah. If you guys want to learn math, this is the place to come. Yes, exactly. If you guys want to join, we do have the Discord server. Here, you guys are free to join. And also, if you've been enjoying this and you want to come around for more math stuff, or if you want to watch me do other things as well, I play games here as well on Twitch. Feel free to leave a follow. It's a good way of getting notifications and you can see more of this. Did I go straight from undergrad to PhD? Yeah, I did. I know for at least for like math majors, and I think for computer science, it is pretty common to go straight from undergrad to PhD. So yeah, I did do that. I did not do my undergrad at GT though. Yeah. So I hope that answers everyone's questions. In the meantime, so we are going to switch over. I'm going to play, but I'm not going to play for too long, because I do need to get to bed early, and I know I wasn't feeling too well, but I'm feeling a little bit better now that we've started to stream. I was feeling like a little sleepy earlier, kind of wanted to fall asleep, but we're going to be playing some Mario Golf. Let me switch around to that 1 second. Thank you, GT. I appreciate it. Have to head out. Yeah, no worries. Thank you for coming by. Where was I? Let me disable this. And let me plug in this. Okay, so we should be getting set up here in just a second. I know a lot of people that came from the raid. I know you guys came from the office hour that was also from Thai earlier. Is that how you pronounce this thing? I hope I'm pronouncing it right. Thai. Or I don't know. I'm not sure how to say the full name either. But if they're still here, I really appreciate the raid again. Yeah, we are going to be switching gears a little bit here. So we're just going to chill here for a little bit. I hope everyone can enjoy the rest of the stream. Let's see, where are we? Oh, I think my thing turned off here. 1 second. It's still black screen. Okay, I apologize for the technical difficulties. We should be getting everything working in a moment here, hopefully. Okay. Yeah. Okay, I'm gonna take a quick break to get another drink. When I come back, yeah, it says Minecraft where we're gonna be playing some golf. We did Minecraft yesterday actually. Let's see, is the audio working here? I don't hear anything. Why can't I hear it? Okay, 1 second here. Okay, we're almost, let's see. Let me set this to, turn off this. Oh, can turn this on? Anyway, I think I almost have it. Okay, will this do it? Okay, I think we got it working. Okay, there we go. Okay, I will be right back. Okay, we are back. I got some vanilla Coke, my favorite Coke. There we go. Let's go ahead and get started here. Hopefully the audio is sounding good for everyone. Just want to double check. Okay, let's go ahead and play. Wait, no, we're doing the adventure mode. Okay. So I know last time that we were playing, we had finished. Oh, I need to update my stream title. 1 second. In the game. Okay. Mario Golf Super Rush. Okay. There we go. Okay, so we're gonna. I normally stream until like 1 a.m. Eastern, but I think I do have some other things I need to do tonight, so I'm probably gonna only be streaming for maybe about another half an hour or so. I apologize, I can't do a full stream tonight. We need to find this master singer guy. Where is he? He is. Oh, they have a drought. That's awful. Oh no! Carry their own water. Okay, let's go talk to this master singer guy. And it's gonna teach us to use the force or something with the ball. We'll see. Hello. Do you know about the tremendous power of energy? Ooh, that sounds fancy. He's like, of course you don't. Wow, that's rude. But he's like, if you could know about it, if I told you about it, you have much to learn. Okay, okay, guy. Sure. Okay, there's 2 things we're gonna learn today. 3 if you count his name. Wow. This guy is full of himself. What the heck? Is the sky blue, is the water wet? The answer to at least one of these may surprise and annoy you. Okay, the goal is to hit the ball onto the island across the water, but the winds are blowing fiercely. How do we do it? Okay. You'd have to shoot a ball at a low trajectory and skim it across the water. That is the goal. Okay. Yeah, we're saying, won't the ball sink if it hits the water? Yeah, that sounds like a reasonable question. Oh, does it? Let me... I thought I updated that, Poppin. Thanks, thank you for popping into the stream, by the way. Glad to have you in as usual. I thought I... Let me check. I might need to reload. Yeah, Poppin, maybe try to refresh the page and see if that updates it for you. I know sometimes, like on the viewer end, sometimes you do need to refresh. It says Mario Golf for you. Alrighty, welcome in, Sleepy. We're just doing some golf in here. I pressed A without reading the dialogue. I totally missed. Okay, whatever. Use this club and see if you can land 3 of 10 shots at the targets on that island. That happens to you. Yeah. Okay, we got a green shell 3-wood. I feel like I accidentally. Oh yeah, it was your yeah. Twitch is weird about that sometimes. Okay, there's some dialogue which I didn't read, which I feel is very important. So we'll see. Oh, okay. I guess it's just a fancy club that we're using. Good. Okay, can I just hit it over this rock? Will that work? No, okay, no. Oh, no, that didn't work at all. Too bad, okay. Can I just do this? I thought I could hit high enough, but I guess not. This is like a low hitting ball here. Oh my gosh, come on. Okay, we're good. We did it, folks. And kablam! Bam. It's interesting, Poppin. You actually came in just as we switched. We were doing like our math office hour earlier, so you missed an exciting presentation about modular arithmetic. Let's see. You passed the first stage of training. Okay. Unleash the energy that already burns within you. This guy, I can't take this master singer seriously here. Okay, ancient energy operates much like a vending machine full of delicious salty potato. Ooh, sounds good. You have to get coins. Okay, I see. So this sounds more like a cult regarding capitalism. Yeah, like you need to get the money, and only then can you get the energy needed to do what you need to do. Okay, we collected enough coins. You unleash a special shot using energy. Okay, try aiming one at that rock. Okay. I'm gonna smash this rock into pieces, I guess. Kablam! Whoa!
Nice.
That was something. Okay. We have 1 point to put. We can add some to our power here, maybe. He's this master singer guy. He's like, "Are you surprised? I'm not. I know all and expect the unexpected. Not that this was unexpected, but jeez." Okay, we have to continue using energy to increase carry and land balls with precision. And press L when the energy gauge is full to use our special shot. Okay, cool. Cool. I did not let that music audio play through. Jeez, we kind of cut it off short there. We can keep the club. Ooh, we use during the lesson as a memento. Or you can keep using it. Yes, sure. Sounds like a useful club. Okay, let's actually do some golfing here. Do an actual competition or something. That was just some practice. Okay, some news. Road to Balmy Dunes is open. Okay. Sure. It's funny, I'm usually the type of person that like talks to like every single NPC in the video game, but like I feel like if I did that for this game, we'd be here just reading dialogue all day and not actually doing any golf. Here, we'll talk to maybe a few people here. Looks like he's enjoying himself here. Yes, a full-fledged resort with a desert oasis. Yeah, okay, we're saying that there's like, been like a drought that we saw earlier, and the heat's severe, haven't been able to host any events. Okay. What about you? Pleasantly hot. That's a good question. What is up with the weather? Let's see. Let's just play some golf here. Speed golf is open. Okay. Okay, we'll do a practice round, I guess. Register for a three-hole practice round. Head over to the first tee when we're ready. Okay. We're gonna do a 3-hole practice round. Oh, a huge boulder is blocking the river. The road is flooded. Well, it's a good thing that we learned whatever thing to break rocks into millions of pieces. So that's how golf works. Keep an eye on the water. Complete 3 holes before time runs out. Okay. Okay, folks here in the desert love seeing how fast they can play while staying hydrated, only from water they carry along. Okay. But the heat wave, if you're out too long, we've got to pull you out for safety reasons. That makes sense. You gotta prove you can get to the oasis fast enough, if not, practice rounds only. So to get a feel for how things work at Balmy Dunes, why don't you take a small water bottle and play 3 holes? Okay, sure. Need a water bottle. Okay. Oh. Cool, we got a little water bottle. That bottle is just the right size for 3 holes, but if you run out, it's game over. So you have to keep an eye on it. Gotcha. Sounds scary. I know we were struggling last time with the last set of, it was like the cross-country golf. I wonder how difficult this is going to be. If it's really going to ramp up in difficulty. Okay, so that's our water. As you see right now, we're 100% water as opposed to the usual 70%. No, no, wait, no. It says in the top that they're 50%. Okay, never mind. We're already dehydrated.
Ready?
Okay. Let's go ahead and. Oh my gosh. So all this dust here. Jesus Christ. Okay, here we go. Just dashing through. Okay, there's the hole. That thing is in the way though. So what we're gonna do, we're gonna try to curve our shot here. Let's do this. Okay. Then we'll curve it and then curve it back, and see how that works. Oh, that's a pretty good shot. Right there. Okay, cool. Come on. Let's see. This is going. There's the same elevation, and it's downhill afterwards. That's fine. Okay, let's try this. Come on. Nice.
Nice birdie.
Oh jeez, already getting low on water here. Okay, I think we should be fine though. We're not being too terribly slow.
Ready?
Oh, we can probably just get a hole in one here. So let me adjust a little bit. Okay, that should be fine. Let's try that. Can I run across here? Yes, I can. Okay. Cool. Where's my ball? There's my ball. Aw. It is here. Can I... I can probably just hit it in... Okay. What is the wind like? Okay, there is some wind. We need to adjust a little bit. We chip it in? No, we can't. Okay. Come on. Nice.
Nice job.
Okay. We still got plenty of water. We should be fine.
Ready?
See these trees. Okay, let's just play it safe. Let's not deal with these trees here. Don't want to deal with the trees.
Nice shot.
Okay. Get these coins. I mean, it is wasting our time a little bit. We should be fine. Okay. That is downhill. I think we could... Oh, the wind is not working in our favor, though. I think we need to... I can have it roll extra far, though. That's a possibility. Do this. Make it... Get some extra roll there. Oh, that's actually pretty good. Oh, come on. Nope, nope. We ran too far. Oh my god, come on, hurry up. We're gonna die.
Birdie.
I think that's not enough. No, okay, we're fine, we're fine. We are good.
Nice.
Okay. Very cool. Let's add it to here, I guess. Cool. So I think there's gonna be like another practice, maybe like a 6-hole practice is my guess afterwards. And now we're ready for 9 holes. Okay. Visit the front desk. Okay. So I think we'll do these 9 holes and then we'll call it a night afterwards. Yeah, I apologize that tonight's a bit of a shorter stream tonight. I do have some other things I need to finish up here tonight, unfortunately. Okay, but let's go ahead and give 9 holes a shot. Oh. So we can rest at the lounge. Yes. It's tea time. Time to have some tea. No. We run out of water, that's the end. Okay. Then we're still running out of water partway through. Great rounds. Do our best to manage water carefully. Okay. Is there a way to get more water though? Do we just need to... Can we just like dive in a lake? That would be nice. Well, it's probably not drinkable water though.
Ready?
Unfortunately. Okay, here we go.
Nice shot.
Okay, here we go. We can try this. I'm a little bit worried about that thing though. We should be fine. Should be fine. We got it. Oh my gosh, no! my. Oh my gosh, I'm dying. Wait, how do I? Wait, get. Oh my god, I'm gonna die. Where's my? Okay, there's my ball. Oh my gosh, no! Oh my, no! I think it's kind of a scary mechanic. It's putting some type of timing on an otherwise chill round, and timing is not one of your strengths. Yeah, this has been a bit rough. Okay. I feel like I was doing good, and then all of a sudden I go into quicksand, and it's like all over. Okay. Oh, this is my stroke 5 already. Oh my gosh. Come on. Nope. Oh, this is not looking good here. I don't know if we can survive 9 rounds. That's the thing. I'm a little bit concerned.
Ready?
Okay, we can at least do a hole-in-one here. That's possible. I'm a little bit worried about that dude, though. Here, let's try to curve our ball. We can curve our ball. It should be fine. We'll just curve it. There we go. We can run across here. Okay, let's try to chip it in. See if that works. Come on. Not quite. Wait, this should just be a straight shot. There we go. Okay, we at least got par. Oh my gosh. We need to beat Toad? I don't know if we need to. I'm not confident. Oh, that's not gonna work. I didn't even look at the wind, I just shot it. Jeez. Okay, I need to focus on actually getting to my ball. Okay, here we go. Oh, I didn't look at the thing, it's curved. Ah, that's not good. Okay, are we on the green? We're close to the green. Let's see. I'm not sure if we can chip it in. Okay, we'll try this. It's probably not enough. Or maybe. Come on. Nope. Oh my baby. Oh, okay, we're good, we're good, we're good.
Nice
Uh
job.
oh no. Do we I'm not sure what the goal here is. Do we just need to finish? Or do we need to also beat Toad? I'm not sure.
Ready?
Can I do this? That looks risky, but let's do it. Let's risk it for the biscuit. Come on. Come on. Okay. Oh yeah, this is not good. Maybe we should try to hit it more on here first, a little bit. Get it actually on out of the bunker, and then we'll hit it far. Oh my gosh! Come on!
Nice.
Come on! Oh my gosh! It's still like not far enough. I did not think this through. Okay, I can maybe hit it over here. It's not looking good though. I'm not liking this. I should have just. I shouldn't have risked it. This is all my fault. Okay. Yeah, I'm not sure what I was thinking. Oh my gosh, come on. Okay, now we can just hit it in, hopefully. See how this is. Come on. Okay. Let's just hit it in here. Nice. At least par.
Nice job.
Okay, we're at 65% water. Cool, cool.
Ready?
Okay, I think we can just hit straight for the most part. It seems pretty straightforward. I just noticed there's all these other things in the way though, so that might mess us up. We'll see. Am I in the bunk? I'm in the bunker. Oh my gosh. I could try to just go for it, but I'm gonna... Oh my gosh, it's gonna be so off. Let's just go for it. Whatever. Let's go. Oh, that's gonna be way off center. Yikes. Oh, it's on... it could be worse. Okay, there's a bit of wind. Let's adjust. Let's see how this is. I think we over-adjusted. There we go. And it's in.
Nice job.
Have some more soda here. A sip. Okay. Yeah, I'm not sure if we need to beat Toad or not, or if we just need to like, just not die. We'll see. Can we get a hole in one? We can try. Let's go, hole in one.
Nice shot.
Oh, nice, my ball's right there. Come on.
Birdie.
Okay, nice. It's in. I was looking a little bit I was looking a little bit scary there. Didn't look like it was gonna go in for a second. Oh no, Toad! What are you doing? Okay. Oh, I think I think we're ahead of Toad now. That's nice. I think we should be fine either way. This whole 7? Okay.
Ready?
I could try to go directly there, but I'm not gonna risk it. That's not worth it. Howdy, hey Ram, how's it going? We're just playing some Mario Golf here. Let's see. I need to hit. Oh wait, I did not look at my surroundings. I'm gonna hit that statue, aren't I? Or maybe not. Maybe not. Maybe we're good. Oh no, wait, I'm in the bunker. Yeah, no, that was not why. Oh my gosh. What? Okay, let's aim this way. Okay, let's aim here. Oh my gosh, this is gonna be an awful shot. Oh my gosh. Okay, here we go.
Nice.
Let's see. Let's use this. Okay, I don't know if I have room to adjust much because of this dude over here, but we'll just try hitting it here. I hope that works. Oh, okay. I need to adjust a little bit here. Is this good? No, okay. That was way too many bad things there. Okay. I think we just hit it straight. There we go. I got a bogey. Oh, you had a great day. That's great to hear, Ram. I'm glad you're having a good day. Hope your weekend was good in general.
Ready?
Yeah, we're just doing just chilling here. We're gonna be ending stream a little bit early, so we're probably gonna be wrapping up after the set of 9 holes here. But it's great to have you in here, even if it's only for the last few minutes here. But still appreciated. No worries. Yeah, I would normally keep stream going for like another hour or so, but I do have I have some other things I need to take care of tonight, unfortunately. Okay. Let's hope this works. Oh, you saw Shang-Chi today. Oh, it's hilarious. Oh, interesting. I haven't heard too many things about that movie other than it's good, which I feel like I should probably learn more about what the actual where am I going? What the actual movie entails. But I'm glad
Birdie.
glad he had a good time. I don't remember what movie I saw last in theaters. I forget what it was. I think it's called like Escape Room 2 or something. It's like a horror. It's like a horror suspense kind of film. It kind of has like Saw vibes, but it's like also like escape room puzzles. That makes sense.
Nice try.
Okay, I think we have one more hole. Okay, I'm not sure if we need to beat Toad or not.
Ready?
Yeah, I did not read the goal. Yeah, I'm not sure if we just need to finish without dehydrating or if we actually need to beat Toad. Bad dad versus good son is the basic plot of the movie. Got it. You can do a lot of things with that premise.
Nice.
Definitely a lot of room there. for some good movies. Okay, let's see. Come on. Ah. I could go this way. I'm not gonna. I don't want to deal with that. That's too risky. Okay, here we go. Oh, no, 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 no. Get out. Must have drowned in the quicksand there. Let's see. Can we get a hole in one? Maybe. Maybe. Let's try it. Ooh, what? Oh, what is this? Okay, this is curving to the left. Make sure to just aim straight. See how that works. Okay, and let's dash over here. Oh, come on. Go up! No! Stop drowning! Oh my gosh, I'm gonna die. Oh, come on. Go up! You're only in with one part because it broke continuity, but that was part of the end credits, so you let it slide. Okay, okay. Oh, this is a far-ass putt. Jesus Christ. I'm like putting from like a mile away. And it's uphill. Jesus Christ. Okay, let's just gun it. Come on. Nope. Oh my gosh. Okay. Can we get it in this stroke? Let's see. I'm not confident. Okay, we got it. We got it. Okay. If it's part of the end credits, then I don't know. I feel like it's not too bad if it's just something in the end credits that people throw in, but yeah.
Nice.
Okay, it says nice, so I guess that means we completed whatever we needed to do. Yeah, 'cause I wasn't sure if we needed to just win without dehydrating, or if we also needed to beat Toad or not. But I think we're good. I'm confused about these stat things. It's saying like I can upgrade it to 10, but if I don't, it goes down to 8. That's so confusing. But okay, whatever. I'm not quite sure how these stat changes are like that, but whatever. Hello, everyone. Wow! Finished the Balmy Dunes front 9 in this heat. I'm amazed. Yeah, of course. Look at this. I have my friendly vanilla Coke to keep me hydrated here. Golfing is no joke. Ask me how I know that. Staying hydrated is important. He died of dehydration. Is that why he's like that there? Jeez. I'm on the next level, yes. Oh, everyone's so impressed. Jeez, I just golfed. That's all I did. Yeah, you should wear your short sleeve suit. That is right. The back 9 is impassable. Okay. What do you mean I have to bring you in ice water? You can get it yourself. Unless he's saying like, oh, you're so good at surviving the heat that I'm gonna have to do everyone's be the water boy for everyone here, fetch everyone drinks. Anyways, like I said before, I am gonna end stream a little bit early, unfortunately. But thank you everyone for dropping by. It was a pleasure having all of you as usual. Those that are new to the channel here, I hope you've also enjoyed yourself here. As you know, yeah, so I know some people came from our math office hour thing that we were doing earlier. But as you see here, we also play games on stream as well. But if you're interested in any of the content that I do, and you want to see more of it, and if you're not already, feel free to drop a follow. It's completely free. But yeah, thank you again for everyone for coming by. So next time we're going to be streaming on Tuesday. Well, I say that I'm actually going to be gone for like a I want to say vacations. It's like a semi-vacation. I'm still going to be working though, but I'm going to be away from home essentially. So I'm not sure if I'm going to be able to... I won't have my full streaming set up. I should be able to... I might be able to stream. We'll see. It kind of depends. So if I am able to stream, I will be streaming next Tuesday. Otherwise, I'll be taking a little bit of a break. And we probably, yeah, if I do end up taking that break, we probably won't be back until next week Saturday. But if you have any questions about that, I might try to update everyone in the Discord. So feel free to follow there for announcements as well. Yeah, thank you again, everyone, for stopping by. Let's see if we can find someone to raid here. 1 second. Let's see. Who can we raid? Let's check this person. Okay, let's try, let's see. So I haven't rated this person in a while, I think. So this person, they're also a VTuber like myself. Well, they're not a penguin VTuber, but they are a VTuber. They're playing a little bit of Apex Legends. So we'll go ahead and visit them. When you go in there, if you want to join in on the raid message, today's raid message will be Penguin Hug, all caps. So feel free to copy and paste that when we go and do the raid here. But let's go ahead and give Mimi some love here. Let's see, type in raid Mimi Naru. Okay. I'll see y'all when I see y'all. I'm not exactly sure when I'll be streaming next, but we'll see. Adios.